So hello, welcome to the Open Shading Language Community Meeting. I'm Larry Gritz. I'm on the TSC and I'm the Chief Architect of OSL. Briefly today, we're going to give a little bit of an introduction to the project. We have a wonderful section from Zach Andersson that is a video giving both an overview of what OSL is all about, sort of from a user perspective, as well as a brilliant demo of what the implementation is looking like from a user experience perspective in 3D Studio Max, which I think is really kind of best of class of these things at this point. We will return to me for a general project update on what our status is and what we've done over the last year since the last of these meetings at SIGGRAPH. We will then go back to Declan and Adrian to talk about the progress on OSL running on the GPU and their experience integrating that into the Arnold renderer. Back to me to finish a little bit of future-looking roadmap for the project, and then hopefully we'll have lots of time left for general Q&A. And Chris Kulla, who is the chair of the TSC and a long-time developer on OSL, will moderate the Q&A for us. Let me start with a little bit of a brief intro and a recap on the important details about the project that everybody here should know. So just in case there are people who are not super familiar with it, you're just passing through, this is your first introduction to the project. Open Shading Language, or OSL, is a domain-specific language that is geared toward describing patterns and materials that you typically find as a way to extend programmability to renderers. Well, they're not exclusively for that, but that's the main target. It's delivered as a software system that is, it's not an end user system that users sort of directly interact with as an app, but rather as a library that different renderers embed in their core to handle the shading. It is an open source project, has been for 11 years under the BSD license. We have a pretty broad participation. We've had over 50 contributors from across the industry. And in case you haven't seen it, here's the GitHub link to go to the heart of the project page. This will eventually be moving, but even when it does, this link will always take you to the right place. So the core design goals for OSL is that we wanted to make a shading language that was really sort of modern and geared toward today's and future physically based path tracers. A lot of the other languages out there that have been used for shading historically had really been designed around much older technology, older rendering methods, and had become a bit of a mismatch to where the rendering field had been going lately. So in particular, some of the things that we changed versus other languages are to make much more of an effort to have a view-independent material description. We compute what we call closures rather than the final lit colors from a particular direction. And that's what gives us a lot of the flexibility. And we, inside the shaders, in an OSL shader, you don't, the shader code itself does not directly loop over lights or cast rays inside the shader. Those things have been pushed back to the renderer. That's where it can really be done better. We base this implementation on a lot of modern compiler technology with LLVM at the heart of that. And that means that we are assembling these shaders on the fly at runtime and jigging all the way down to direct machine code that can be executed very quickly down to the hardware level. And yet we keep the language itself really free from any kind of hardware specific idioms. So we're trying very hard not to tie it to any current hardware, anything that might change. We want these things to last, and as well to not have very many artifacts that would make you need to be especially aware of which renderer you're running on. There are some details, of course, that creep in, but in general, the language is meant to not reflect any particular renderer or rendering algorithm. And of course, it's all open source. A brief idea of the timeline for people who are new. At Sony ImageWorks, we were starting to look at this as a project, really as an internal project back around mid-2008. By the time it was really starting to take shape as a company, we were becoming very committed to open source projects, and this became one of our early ones. So we announced that it would be an open source project in the summer of 2009. By the following winter, the code was live. I think we're on Google Code at the time and later switched to GitHub. The following summer in 2010, Chris, myself, Cliff Stein, and Alex Conti gave a SIGGRAPH talk really laying out a bunch of the details. And following that, we were actually working on getting production ready, and the first real movie that we saw released that was relying completely on OSL was Men in Black 3 in 2012. So if that was our childhood, the adolescence was a whirlwind of our little project getting picked up by more and more studios, embedded in more and more commercial and other products. And in 2017, this work was awarded an Academy SciTech Award to recognize, how transformative it had been. Earlier this year, we also applied for adoption as an Academy Software Foundation project, which we now are. So where will you see this in the wild? The majority of the high-end film-oriented commercial renderers now have various levels of support, including for many of them, OSL being the sole or primary method for programmable shading and patterns. It's also the shading system in a variety of studio internal renderers and in a growing number of open source projects as well. Just the films that we super surely know about, we're kind of well over 120 or so films that are OSL based. The actual number is probably vastly greater than that because OSL is embedded in so many renderers. People just use it as a matter of course, and it's actually quite hard for us to keep track of all the projects they use it on. So with that, I would like to play the video from Zap that goes much more eloquently than me into user perspective and really shows off, I think, what OSL can be for a more comprehensive system.
Hello, I'm Zap Andersson from Autodesk. Today I'm going to do a little introduction to OSL and I'm going to exemplify that with the implementation in 3D Studio Max. So what is OSL? Well, it stands obviously from Open Shading Language, and Larry made it, of course. But what's a shading language? Well, it's basically a way to make procedural fun things happen with your objects without relying on textures. So what you're seeing here, the steampunk teapot or the knotted wood, these are not bitmap textures. These are pieces of code that generate this appearance. That's what you can do with the shader. Now, in classic shader writer, you basically have to write one for every renderer. There were lots of different kinds. So for instance, you had to write something in C++, run it through a slow C compiler, and maybe you get the DLL that you can only load when the application starts, having your iteration cycle be really slow. Or if you wrote something in HLSL, you would take a different compiler and a different pipeline, and maybe for some other render it was still C++, but it was different, maybe different compiler, other DLL, incompatible DLLs, completely different syntax of the shader. It was kind of a mess. And how this applies to Max is that you see on the top line, that's what you do for the shaders for the Max C++ API, and the renders such as the built-in scanline or other renders built on that API like V-Ray or Corona will be served by that approach. The middle line is what you would need to do for the Nitrous viewport, which runs HLSL, and the bottom line is what you would have to do for renders that were external to Max, like Arnold or Mental Ray or whatever. So basically you have to write everything 4 or 5 times. But with OSL, you write your shader once, run it through the really quick OSL compiler, and it turns into a thing called an OSO, which can be loaded at runtime, no waiting for an application. A bunch of OSOs are plugged together in a shading group and sent to LLVM, which performs magic and turns this into running code and sends to the renderer. But you can also take the OSOs themselves and information from the shading group and transcode them into some other shading language, like, for instance, HLSL. Or if you have a third-party renderer, plug-in renderer to your application that you don't have control over, but it accepts OSL, well, just send it the OSL, the renderer does whatever it wants, and then it works. So in the 3ds Max context, the top line again covers the C++ shaders, so Scanline, V-Ray, Corona. The middle line does the viewport, and the bottom line does external renders or renders that translate their scenes and not using the Max API, like for instance Arnold, or maybe V-Ray in GPU mode, or many other examples. So one funny thing with OSL, though, in spite of being called a shading language, it doesn't actually shade anything. Normal shading language tends to look like on the left. There's loops over lights, there's a bunch of ray tracing going on, and all this kind of stuff to make material. But in OSL, you use something known as closures. You basically tell the renderer, I want this much diffuse and this much Phong or whatever. And the renderer figures this out. This has a giant benefit. It moves the actual algorithm into the rendering side. So if it's a VR engine, for instance, it can fake glossy reflections with blurry environments. It has one giant drawback, though. The closures are not standardized. So if you look at a classic OSL shade tree here, which contains a bunch of texturing shaders which send quite normal data back and forth, like points and colors or whatever, they somewhere go into a surface shader, and what comes out of the surface shader is a closure, and that goes to the renderer. The way we solve this in Max is that we actually intercede before the surface shader. We take colors and this kind of stuff from OSL, but the surface shader is based on native code. So it's basically the Autodesk standard surface, or as it's known in Max, the physical material that the renderer runs natively. So we don't support closures for now, at least in Max. So OSL itself is only used for textures, not materials. The benefit here is, of course, you have one shader and it runs everywhere. Real time in the viewport, offline, on your render farm, wherever. And we can switch renderers because we do the surface shader bit natively. We can switch and get the same appearance. We don't care if Arnold have different closures than V-Ray because we don't use them. Of course, this all gives a very quick development time for shaders, and they're easy to deploy. It's just a text file. So what do we have in Max? Well, Max has a built-in OSL editor, syntax highlighting, all sorts of things. You just hit the compile button and it immediately happens. Since we have the automatic transcoding for the viewport, this actually happens straight in the viewport interactively. You don't even need to hit the render button to develop OSL shaders in Max. Also, we embed the OSL source in the scene. So when I send the file to you or to a render farm, you'll never run into the problem of, oh, I'm missing shader X. It's always in there. We also build UI automatically for the shaders, but we also added the option to build a Qt.ui file. You use Qt Designer and build the user interface, and then that user interface can simply be used on the shader. We also support dynamic UI in some cases. So you can have these action buttons that run scripts that actually modifies the shaders at runtime. And for instance, in this case, adds removes inputs to a gradient shader. Pretty clever. Actually, the entire prototype for the Material X implementation is Max that you will see in the Material X BOF, spoiler, is completely done via OSL. So 3ds Max 2021 Update 2 ships with 135 OSL shaders. And I'm going to show you a couple of those real quick now. For instance, we have this environment mapping shader that allows ground projections. It flattens out the bottom of the environment so it looks like objects are standing properly on the ground. Quite nice. We also have this HDRI light designer where you can basically add in images of lights and treat them as light cards. They basically add to the environment, and we can even interactively drag reflections of the light on the surface. Very nice little feature. We have our cool texture lookup randomizer, which removes all repetitiveness from your textures. So this is also very cool. So you can use like a single square of gravel and fill a whole gravel road or whatever. We have the Uber noise, which basically is all the noises at the same time. Much fun. And we do texture projection. You can project, and of course it works interactively in the viewport. Did I mention that before? And of course, me being me, there's a sushi shader. So, you want to play with any of this? Well, you can check out the trial version of Max, of course, but you can also join the beta. That's where all the fun is. You can also check on the Max OSL GitHub. All our shaders are Apache 2.0. And the OSL Shaders Facebook group. Follow me on Twitter if you want. And of course, I didn't put any links in because if you literally Google any of those things, the first hit is the right link. So let's do that. That's all for me. Zap out. Bye-bye.
Great. So with that, I'll give a bit of a project update of the most important things that have happened in our world in the last year for OSL. A big one for us is the transfer of the project to the Academy Software Foundation. Very close to the beginning of the year, we submitted an application. This was not a project that was unknown to the foundation, and it was unanimously accepted with much fanfare in short order. I think this was one of the projects that many people had always wished would come on board. But what does that mean for us as a project and a community? Mostly extremely good things. I think it will really turbocharge our efforts. So the first thing is, rather than being an ad hoc organization where the project was sponsored by one company, even though we always took contributions from anyone, really, part of the purpose of going into the foundation is to sort of dispel this idea that it's one company's project and everyone else is just a user. We really are very committed to making this an industry project. Lots of people depend on this. There are many stakeholders, and they really should all have a hand in steering it, in contributing to it, and feeling a joint ownership, so that it's not dependent on just me or just the company that I work for in any way. So we now have a formal charter and a set of governance rules. You can actually, the documents that define both of those are just in the repo. They're pretty easy to find. And we have a technical steering committee. The TSC, as we call it, consists of a number of representatives from many studios and software vendors that were the big stakeholders. And we meet every second week with the Zoom call. The meetings aren't open. They're on the ASWF calendar. Anyone is welcome to join, whether it's just as an observer or a participant. All are welcome here. And there's not really any magic to who's on the TSC either. Basically, if you're a major contributor with the track record, or your company is a major user or integrator of this technology, and you feel like you have an important stake in it, that's basically the path to getting representation here. So in addition to the TSC and sort of formal governance documents, we've also switched mail lists away from an old Google group and to an ASWF managed mail list. We will have a new set of contributor license agreements that will get voted on and take effect shortly. So even if you've been a contributor in the past, you might have to sign a new CLA when that is done, coming up soon. It is very similar to the one we used before. It's based on Apache 2. There's some really minor differences, but no new food groups here. the CLA that we used when it was in an ImageWorks project is very close to identical. So hopefully this should just sail through your organizations. After that is done and a couple of other remaining paperwork issues, we will move the project from the ImageWorks GitHub account to the Academy Software Foundation GitHub account. The old one will redirect, so don't worry about anything getting lost along the way, but we will officially move it to be a direct sibling of the other ASWF projects. And we are also, officially we're in what they call an incubating project, but what we really want to do is move to graduation to be a fully adult project under the ASWF. And a very important part of that is going to be committer diversity. We talk about diversity a lot, but in this context, I'm actually not talking about demographic diversity, which of course we also are very committed to. But in this case, this is diversity of participants as being multiple people, lots of people who know how things work, representatives of many companies. So this is the risk mitigation that is part of the purpose of putting the project into this organization. It is making sure that if something happens to an existing one or a couple of key developers, or if they're distracted by things at work, or if one company that's running a project doesn't have the resources or the interest, it is not putting everyone else in the industry who's dependent on the project in some kind of very risky position, right? It's spreading the responsibility and the knowledge and the contributions across the stakeholders in a more even way, so that there's very low risk from any one person or any one company being able to jeopardize the project. And I don't mean through any malicious way. I just mean, people's attentions and abilities to contribute wax and wane, and we don't want that to hold up all of the many uses. Another big thing that is going on in OSL is we have finally are in the middle of a 1.11 release. This is long overdue. We apologize for that. We have not had although we do minor, sort of patch, fixes and minor enhancements, sort of style releases, approximately monthly. The big changes that introduce new features and can potentially break compatibility, we only do every once in a while. And unfortunately, we have not had one of those since the end of 2018, I'm sorry to say, which means that a lot of great features and improvements that have been locked up in the development branch have not made it into a supported official release for quite some time. We've been in beta now since the beginning of the month. I just tagged a release candidate last night. I hope that means that there won't be any other changes other than critical bug fixes between now and the beginning of September, when we'll call it the official release. Then that will be the supported release branch, and the older 1.10 and older will be obsolete and will really only be patched if there are emergencies. Meanwhile, in the main development branch, that is where all the big changes continue to happen. So highlights of this release, from the language standpoint, someone who is writing OSL shader source code, probably the biggest convenience factor that you'll see is that we've finally allowed components of colors and vectors and points and so on to be addressed by the field names, like .x, .y, .z, .r, .g, .b, and so on. You used to have to use the subscripting notation, which still works, but a lot of people like this, so we added it. There have also been a bunch of OSLC compilers improvements in the handling of polymorphic functions. Polymorphic means there are multiple functions with the same name, but they take different arguments. And sometimes you can get yourself into cases where the arguments you try to pass could potentially match more than one function signature or have ambiguity. And so there was a big overhaul where we greatly improved the consistency of how we resolve which of the polymorphic functions it chooses for you, and greatly improves the error messages that you get if you do something that's ambiguous and it's not sure what to do. A few important dependencies have changed. I'm only talking about changes in minimum dependencies here. Of course, as compilers and other libraries that we depend on advance, we're always making the changes to support the newer versions of those. That's not what I'm talking about at the moment. This is about things that we're dropping support for. So right now, one of the biggest, baddest dependencies we have is LLVM. And so for 1.11, the LLVM versions we're supporting are LLVM 7 through 11. So we've added several new versions, but we've also dropped the old LLVM 4, 5, and 6. And primarily that's because they are lacking some support for features that we are needing for some of our forward-moving work. Also, OpenImageIO is a major dependency, and I hope this isn't too controversial, but we've dropped the old 1.x support. It's got to be OpenImageIO 2.0 or above for this release. That's already 2 years old, so I don't think this should be a big thing for people. Also, our build system for quite some time has been dependent on CMake, but in this release, we bumped the mandatory minimum to 3.12, and because we take a lot of advantage of that to simplify a lot of the build scripts. As far as internal changes that renderer authors will appreciate, we have changed the way through the API that you specify shader groups to have thread-safe versions, so you can have multiple threads setting up shader groups in parallel. They're not stateful anymore. And we've improved, as always, some of the runtime optimization, so your shader should run a little faster. And we've also improved the JIT time, so that startup time that we're generating machine code from the shaders at runtime. And it's not really supported features in this version, but along the road here, we've made a lot of progress on the both the batch shading and the GPU projects, which I'll talk about shortly. So that was recap. Let's talk a little bit about roadmap and future. So as I just referred to, the two big transformative subprojects that are in progress right now are a batch shading mode based on CPU SIMD instructions and a GPU shading mode primarily targeted at OptiX. So this batch shading, this is work that is being led by Intel and Pixar. The lead author on that is Alex Wells from Intel. The idea here is that the old style primary interface to OSL from a renderer standpoint of getting it to shade things is you're shading a point at a time. And so this is presenting a second interface where you can shade collections of either 8 or 16 points at a time, and do so very efficiently by taking advantage of SIMD hardware that can do 8 or 16 wide operations in one instruction each on some of the newer CPU hardware. And so, very, very basically, we're in isolated shader only tests, we're seeing between a 2x and sometimes faster than 16x speed up, where we're really isolating these particular things. In the context of a larger renderer, there are many factors that affect performance, and of course shading isn't all of rendering time, it's just a fraction of that. So like I said, this has been implemented already in RenderMan and used in production at Pixar, and so they have been reporting that in sort of old style RenderMan tests, they're seeing about a 1.2x factor improvement when using the SIMD instructions. For a newer research initiative they have called RenderMan XPU, look for their talks on this, they're seeing more like a 1.7 or better x speed up. Like this is all told, this isn't just isolated the shading time. And this is for some tests they were doing of fully shaded objects in the real scene. This is in a private branch, and it was based off a slightly older version of OSL. So we're in the process of a big project to slowly port the pieces back to the current OSL mainline. And so we've got a lot of it there. All the pieces aren't there, but it's an ongoing project. So certainly the next major release should have this fully working. And if you snapshot this or go back and look at the video, there is a talk that Intel and Pixar did about some of the gory technical details. If you're really into that stuff, I recommend it. The other big project is GPU sharing. The trend among all of these high-end film renderers is that at long last, they're all in various stages of having GPU ports, largely based on NVIDIA's OptiX ray tracing toolkit. And so that is the primary target right now for direct GPU support of OSL. So currently we have quite a bit of it working. A lot of basic shaders just work with both OptiX 6 and 7, but there is not complete support of everything you can do in OSL. And in fact, there's a lot of work that we still need to do to really support it all well. This is an ongoing project. So what I would like to do now actually is switch to Adrien and Declan. They also have some video and material to present that will flesh out a little bit more about the state of this project, and in particular, how its current shape in Arnold rendering. So I'm gonna unshare my screen, and Adrian's gonna take over.
Hi everyone, I'm Adrien. I'm the Arnold core lead at Autodesk, and I'll be co-presenting with Declan, also an Arnold core developer. So we're going to talk about the status of the OSL GPU project, and then we're going to talk about what's the status in Arnold, and we're going also to talk about like how different tricks to integrate the OSL GPU project into your renderer, and the few caveats that are still there, and then we'll end up by showing off the Arnold GPU in a demo. Okay, so OSL GPU was initially contributed by NVIDIA. The first pull request was in 2018, I think, and it's been steadily improving since. And I really want to thank Tim Grant from NVIDIA, who contributed the first pull request and has been super active in fixing bugs and adding features. So currently, OSL GPU is fully integrated in the current OSL in master. If you're building OSL from master, you simply build with OptiX. It relies on the NVPX LLM backend. Most of the easy native shade ops in OSL are supported. What requires a bit more work if you're integrating OSL GPU in your own renderer is all the shade ops that are depending on the renderer services or platform dependent, like printfs and stuff like that. For those, you do have to send your own LLVM bitcode to the OSL shading system. So yeah, a bit more work, but as you all know, like GPU programming is harder. That's a constant. The main limitations are really the absence of dynamic strings and string arrays. Those require some sort of global locks and memory allocation, which never good on CPU, although some people would argue that it's not a good idea on CPU either, and are actually glad that this limitation exists. So it's ongoing debates. And for the status of the project, one major contribution that was added recently is OptiX 7 support, like basic OptiX 7 support, which is going to be, if you all know, OptiX 7 is the big rewrite of the OptiX API. It's completely breaking. It's new and modern way of using OptiX, and it's really the way to go forward. So Arnold, so as you all know, probably Arnold is a path tracing production renderer. Arnold has been fully compatible with OSL. We have full support for OSL, not just patterns, like we also support closures. And so it was super important when we introduced Arnold GPU that we were also supporting OSL on the GPU. And we released Arnold with GPU support and OSL GPU support last year at SIGGRAPH. At first, it was like with very basic OSL functionality. And we've been adding, building up on top of what we had, and adding support for more and more OSL features until last month when we released Arnold 604 with ray tracing in OSL and attribute queries. And then I'll hand over to Declan, who is going to talk a bit more about how we integrated OSL GPU into Arnold.
Okay, so here's a kind of basic overview of how the OSL GPU pipeline works. If you've implemented a OSL on the CPU in your renderer before, this is all going to be quite familiar. So you have your OSL, you create your shader group, which is like a shading network, and then you give it to the OSL runtime. The OSL runtime jits all this and then produces some machine code. On the GPU, this is in the form of a callable program. This is a OptiX feature, which is functionally equivalent to a function pointer, but it runs on the GPU. And then at execution time, it's very similar to the CPU. You set up your shader globals, you execute your shader group in the GPU. This will be your callable program, and then you read the outputs after your callable program is run. So let's take a little bit more of a deeper look at what's going on in the compilation. So when OSL JIT compiles your OSL code on the GPU, we take some of your render specific shading ops, which you pre-compile into LLVM bitcode. Then OSL turns this all into its LLVM immediate representation, and then hands it to the LLVM NVPTX backend, which produces PTX, which is like a ASCII-based assembly-like language for NVIDIA cards. And then this PTX is given to OptiX, which is then JIT compiled again and turned into your callable program that you can then call when you run your OptiX renderer. So this is where some of the challenges sort of start. The generating GPU code can be a lot more expensive than CPU code. For starter, there's one more level of indirection from where, like on the CPU, you would just compile your code into like machine code and then run. Here we go to PTX and then OptiX and then the callable program. We have to compile everything up front. We can't do it lazily because everything has to be done before the GPU kernel launches. GPU PTX takes longer to compile anyway because it more aggressively inlines and optimizes code. Currently, there's a limitation with the NVPTX backend where you can't compile stuff in parallel, which makes the problem even more difficult, as we're seeing some shaders take minutes to compile, and the fact that we can't do this in parallel makes it even longer, and it's wrecking sort of time to first pixel and makes IPR pretty painful. So we've done some things in Arnold to kind of mitigate this compile time. So how do we do this? Well, the problem is that we have too much LLVM bitcode. Like some of this is coming from the OSL code that your user is providing to the renderer, but most of it is coming from shading ops, which are being inlined over and over again, and you're just producing huge amounts of code. So how do we solve this? Well, the simple answer is we want to compile less code. So you can do some simple stuff like reduce any redundant code you may have written, or try and reduce the amount of templates you're using, which generate a lot of code. But the main thing, well, the best thing that we found worked was to take advantage of some of OptiX's features, this callable program, and move some of the logic there. So these callable programs generated by OptiX are, once they're compiled by OptiX, they're cached to disk, and then you don't need to recompile them later. You can then just call them straight away. So what we do is we move the logic from OSL's shade ops into these callable programs, and then just call them from the shade ops. So this reduces the amount of code that's actually JIT compiled by OSL significantly. So see on the left, we would have a traditional kind of OSL shade op, which has many lines of code, and this effectively turns into 2 lines of code. There is still an investigation to go on about with this indirection, like there's not going to be as much lines of code inlined when you get JIT compile. So there might be some performance loss, but we haven't really found that in our results so far. So let's look at the numbers using one of Zap's shaders that he mentioned earlier from Max. So we're using the randomized bitmap shader. It's got 5 texture calls, get attribute call, and a get texture info call. So this used to take about 9.5 seconds, and then we've done all our optimizations, and it's taking about 1.2 seconds, which is roughly a 7.8 times speed up, which is great, but compared to CPU, we're still orders of magnitude away, and we need to do better, which we're still working on. So other things we can look at improving is there's some balance to investigate between LLVM and OptiX, because OptiX is also JIT compiling the code. There's some argument that we don't need to JIT compile it in LLVM because some of these optimizations might be redundant and redone. However, if you don't do any optimization in LLVM, then you're not doing any dead code elimination, and you're just giving OptiX heaps and heaps of PTX, which it just has to deal with, which would also be a bottleneck eventually. So some other caveats that are still sort of open problems is the current attribute and user data binding mechanism isn't very GPU friendly. It's very flexible in OSL, but it's still there's a lot of performance that could be improved, because at the moment it pretty much just requires a lot of like dictionary lookups, a lot of random memory accesses, and this is the same on the GPU. There's a really interesting proposal by Luke Emerers from Animal Logic on the OSL mailing list, which is definitely worth checking out. Basically, we just you write all your known attributes to a predefined memory block as much as you can up front, and then when you need these like dynamic lookups, because you can't know what you need, then we drop back to this sort of slow dynamic dictionary lookup case. So now I have a demo of OSL running on the GPU in Arnold in Maya using M2A's OSL editor. So here we have our robot with a simple shading network applied. The shading network has an OSL shader, some Arnold shaders, and this is all running on the GPU. This is a good example of the level of support we had for OSL on the GPU last year. So we have some closures, we have simple arithmetic, we have Arnold and OSL shader interop, and we can run the same thing on the CPU and expect the same result. This was a good starting point for us. For the GPU, we could expose a way for users to write custom patterns and stuff, but there were some big parts of OSL that were still missing. We've implemented over the last year. So first off, I'm going to show off some attributes which were added in 604. So previously, I've added some user data to this mesh to drive the color of each metal plate, and we're going to use the OSL's get attribute function to grab this color and drive the color of our metal shader. So we're just going to call attribute on the attribute metal color. I'm going to go ahead and compile that. And now, once it is all jitted by OSL, start rendering and see the result. So as you can see now, the color is being grabbed by the mesh and is driving the color of our metal. So this is looking a bit too new for my liking. We kind of want this robot to look a bit more like old and worn out. So we're going to do something a bit more complicated. So previously I've written this shader that it basically does the same thing as our last shader, but it also has a diffuse closure, which is being driven by dirt color and a rust color, and then we have some weights applied to both of these. So we could, for instance, up the weight of the dirt and compile the shader again. And then once it's jittered, we're going to see basically there's going to be like a diffuse brown layer across our surface too. So this doesn't look too realistic. We kind of want to break up our dirt a little bit. So we're going to use a texture to do this. So I have this sort of like grunge texture on my system, and we're going to use this to mask our dirt. So simply have get the file path, and then we're just going to call OSL's texture function on the file, compile our shader again, and now we have our texture driving the weight of the dirt on our texture, and we can of course switch back to CPU and we'll get the same result. So I also want to add some like rust to this mesh. I kind of want it to fall in these sort of corners where the plates of the metal meet, and to do that we're going to use a trace tool. So I previously written this function to do this. Essentially it just traces rays from the shading point around near points of that surface, and then just gets the average angle between the normals, and then we normalize that between 0 and 1. So we're just simply going to call this function on our rust weight. Then we're going to compile our shader again, and then we're going to go ahead and jit this. And then because this is using a tracing tool, this can take a little bit longer because OptiX has to recompile the whole shading network for tracing shaders. But once it's done, we'll see the result. So as you can see now, we have some nice sort of like orange sort of rust in the edges where these plates are meeting, and our old kind of robot is looking nice and it's done. So, cool. Cheers, and back to you, Larry.
Great. Okay, let me reshare my screen. Great. So just to really briefly talk about some other smaller things that are on our roadmap, we will be working on built-in 2 and 4 vectors, largely so that we can play a little bit better in the Material X ecosystem. Right now, they're implemented as structs and classes in OSL, but we want to make those into built-ins and be first-class types. As just referred to, there is a plan afoot to change the way renderers explain to OSL what the memory layout is of various things that it needs, and so the shaders will then JIT in such a way that they just directly pull or write to those areas instead of. This will eliminate a lot of data shuffling and copying, and they've done a similar thing in the OSL implementation at Animal Logic and report a substantial performance improvement from it. And then there are a variety of other odds and ends that will get us in full compliance for graduation in the foundation, and an endless array of other small tasks and whatever other features we think of in the future that we want to put in. So if you're thinking, this looks like an interesting project to get involved with, there is no shortage of ways to help. We need all the hands that we can get. Look for us on the mail list and subscribe. Watch the issues on the GitHub. There's an open invitation for anyone to join the technical steering committee meetings. And the bottom line is, as they like to say in the Linux Foundation, this is a duocracy. You get capital in this organization by actually chipping in and making things happen. You know, we talk about this, but like many of us on the TSE and other people involved, this isn't just a hobby for us. This is a part of our jobs, and so that's another route to get involved with these things. And I can't speak for any of the other companies, but I know that at my place, we're actually hiring right now for engineers in a variety of ways, including for both shader development and renderer development, and both of those are areas where one would directly be involved with this project. I'd also like to direct you to a couple of other things coming up over the next week or so related to OSL at SIGGRAPH. I encourage you to look at the physically based shading and theory and practice course that is live on Wednesday. Not only is that just a great set of topics generally, but TSC member and ImageWorks head of shading Lee Curley is one of the speakers there. There's also a really interesting SIGGRAPH talk I just watched yesterday on demand from Pixar about their use of open shading language for procedural geometry. I thought that was super interesting. I didn't know a thing about it until I saw it on the SIGGRAPH program, which I would like to think speaks for the implementability of such things without having to beg for too much help from us. They did it all, and it's quite a neat set of tools. So with that, for the rest of our time, let's just open it to any Q&A or discussion, and yeah, how about it? Let me unshare, and we can all switch to our faces again. If I can find my mouse. There we go.
Okay, well, thanks, guys. That was great. I am looking at the Q&A box right here. I don't see any Q&A. I don't see any questions lined up yet, but feel free, don't be shy. Ask any questions you might have about OSL. So, okay, one question that just came in, how does SPIR-V relate to OSL, and what might we see there in the future?
Yeah, maybe I'll take it.
Yeah.
So SPIR-V is another one of these sort of abstracted kind of assembly languages, virtually speaking, that is the basis of going to a lot of the other non-CUDA hardware implementations. I think in the Material X talk that we just saw, they were talking about a SPIR-V generator for Material X that unlocks access to Vulkan and Metal and other such things. I think that would be great. I think that that we could have something like that as an alternate back end in much the same way that we have CUDA and other things as a back end, and maybe similar to some of the way that Zap's team has done the transcoding to get to, I think it was HLSL in Max, to have viewport visualization of OSL shaders. I think that is just a project that is waiting for a champion to step forward and want to both advocate for it and help organize and tackle some of the work. But architecturally speaking, I think we know where it fits in, and we just lack the hands to do it all at the same time as these major projects, unless some other people can help out, which we would love to have. But I think that's a really important project. I think it would be the key to more people sort of being able to do the stuff that Zap was showing in 3D Studio Max, where you can have like full viewport OSL shaders, but without everyone who wants that having to completely re-implement it as Zap's team has done. That's a pretty high bar, and that's sort of the point in my mind of these open source projects is it gives us the ability to do some of these hard tasks once and then have many products and studios and other projects use them without having to redo them from the ground up.
Yeah, that's great. So what GPU CI capabilities would help OSL? I mean, I can take a stab maybe by saying that I think the main thing, like Larry alluded to in the talk, the main thing we're developing is an OptiX CUDA backend, and that specifically ties to, at the minimum, requires some kind of CUDA capable hardware, and ideally something with RTX support as well. So that's kind of what we're hoping to see there.
Yeah, I know through tangential association with the Open Color IO project that they are working on getting GPU CI, because they have a CPU path and a GPU path. They're a little different because their GPU is based on OpenGL functionality. But in the course of trying to make this work, they're basically finding ways to work into their CI the provisioning of Amazon cloud instances that have the GPUs that they need. And so this is another one of those benefits of being part of the ASWF is we're going to wait for them to figure some of those details out and then draft off of everything they've learned to set those up. GitHub, we're using GitHub Actions CI for our CI right now. On their roadmap, they mention GPUs. It's not clear exactly when those will come, if they'll be kind of in time for us, or if we have to do more of this, provisioning the instances that we need as kind of a special route. But if someone knows about how this stuff works and wants to tackle it, it would be hugely helpful. Like, we've already had problems where we've accidentally checked things in from someone who didn't thoroughly test the GPU path and it broke it in some subtle way. Even if you're not working on the GPU stuff itself, just knowing that as you submit the pull requests, that it's going through CI tests and it's not breaking anything on the GPU path is just would be a huge step forward.
Yeah, that makes sense. So one more question. How does Material X relate to OSL?
I can maybe start to answer that question. So Material X is essentially a higher level than OSL. Material X will describe like whole materials and shading networks, and so it's kind of a very high level XML based representation. Now OSL will be a backend for whatever shaders are generated by Material X. For example, if you load a Material X file in Arnold right now, it will rely on the OSL code gen to render the material as specified. So they overlap slightly in some ways, but in general, like Material X is higher level than OSL.
I think perhaps of OSL as being the primary thing that Material X is targeting as it generates things that will execute the Material X description. So we're an important part of their ecosystem and vice versa, but we're kind of adjacent to each other rather than either one really trying to do what the other does. But they play well together, and we want to further that relationship.
We're pretty short on time, so for whatever questions we don't get to, we'll point people to the Slack channel. But if we have a minute, maybe you can say something about any other GPU backends. Larry?
Sorry, was that a question for me?
Yeah, other GPU backends.
Other GPU backends. Yeah, I think we're waiting for people to suggest what they should be. The main GPU effort we have going right now, the primary target is CUDA and OptiX. It would be great to have more. It requires a champion.
Okay. Okay, so I think that's a wrap on the questions we have so far. Like I said, if you have more questions, feel free to meet us on Slack. And I think think that covers it for today.
Great.
Thank you all for
Thanks
joining.
all the panelists.
Yeah, thanks guys.
Thanks.